All right, so we're going to go ahead and finish up section 2.1 here. So average rate of change and secant lines. So first off, take a look at this video that's here for you. Copy and paste it or type it in and go take a look at that for talking about the rate of change formula and how it relates to slope. But just real quick here, if we have our graph like this, and we've got that this is f of x, this is our vertical axis, it's our function, and then this is our x-axis, our input, and then the f of x is our output, and we have some curve going on this thing, some curve, and we look at 2 points on this curve, right? We look at 2 points, and what we can do is draw in a secant line between those 2 points. Secant. Okay? And if we look at these 2 points, we can say, all right, this here is our x1 position. So this is very similar to what we just did on the last page. And then what we're going to do is look over here at this point. I didn't make this long enough. Hold on a second. Let me extend this out. Here's x. Okay? And then we extend over here. Well, this length right here, this distance, we're going to call this h. Okay? That's h. And so this would be x1 plus h, is that position over there. And then if we come back and look over here, all right, this point here is just going to be f of x1. So we're plugging in whatever this x1 value is right here. We're going to plug it in there and get our y value essentially. And then if we come this way with this one, okay, this is going to be f of x1 plus h. And so hopefully you remember this from back in pre-calculus, but essentially what we get is average rate of change over this line, over this distance. So in other words, the slope of that secant line is going to be delta y over delta x. Again, very similar to what we did in the last video there, the last page with delta y over delta t instead, we did before. And so now this is f of x plus h. We don't need to necessarily name it x1. It's just any x that we pick. So I don't have to have x1 on there necessarily because we have no other x's that are in it. So we'll just go with f of x. And then this is minus f of x plus h over f minus f of x. So that's like y2 minus y1 over x2 minus x1. Well, x2 is x plus h. And then x1 is just x. And again, I don't need that 1 right there. There we go. And so I have an x plus h minus x, so the x's will cancel, and I'll be left with f of x plus h minus f of x over h. Okay, and if you had me for pre-calculus, you know that I said that this was actually a very important formula that you'd need in the future, and then we need this to be the situation where this does not equal 0. So like I said before, this was a very important equation that we'd be coming back to it and in calculus, and here it is. There you go. All right, so let's look at defining the slope of a curve. So the idea is we can look at these secant lines and we can get slopes between 2 points or averages. Well, what if we want to know exactly what was happening? Say this was a graph of a car speeding up. Now, we could say it started from a red light and started speeding up. We could say how fast, what was its average speed between 0 and 2 seconds, or 0 and 3 seconds, or 3 and 4 seconds, stuff like that. But what if we wanted to know how fast was it actually going at 3 seconds? What was its speed after 3 seconds? Not its average after 3 seconds or between 2 and 3 seconds, but right at 3 seconds. How fast was it going at that moment? And this is where we need something like this, where we can look at a point not at an average around it, but rather right at it. So if you look here, we can start and you look and you see this right here. Okay, see that one right there? I just darkened in. That would be the average between P and Q. And so that might be something kind of close to what the actual speed was, or the actual rate of change or slope was at P, but we can get better. And we can get better by moving Q closer to P. So the next line, if I did another one, let's get another color, this one would be even closer, right? That would be closer to what the actual average was at P. And then I can move even closer. I can keep moving closer. And I get that next line right there, which I guess I can do in green here. And then this one, I get the slope of this line right there, and it'd be even closer. And then I want to move even closer. And so the next one would be the slope of this line right there, that yellow one. Okay? Until we eventually make it to that red line, right? So if I get rid of all this jumble on here, what you eventually get to is this red line right here, as we keep moving Q closer and closer. In other words, we're putting Q like right there up against P. And so what we'll end up with is the slope of the tangent line at that point. And we could even do the same thing coming from the other direction. We could start with Q on this side and start moving Q closer until we got Q really, really, really close as we possibly can. Keep pushing it closer and closer to P. So like if we zoomed way in, down to where you could see individual points, like P and Q would be like the 2 points that were right next to each other, the closest we can possibly get to P, right? And then what we'd end up with is, again, this tangent line, and it would be the same as the tangent line when we came from the other side. Okay, so we can basically push Q over to being right next to P from either side on this one. Okay, so let's take a look. Let's try this. Let's say, find the slope of the parabola y equals x squared at the point 2, 4. Write an equation for the tangent line at P. So if we look at this, here's the function y equals x squared. And what it is a nice parabola, something like that, let's say. And what we're looking at is the point 2. There's 1, 1, 2, 1, 2, 3, 4. So something like that. Okay, this is what we're looking at. This is the point 2, 4. And so what we want to do is we want to pick something. You're basically going to pick a Q that's, say, up here, and then we're going to take that Q point, right, Q, and we're going to push it down really close, such that Q ends up right there next to it, and we have this really, really tiny h, really, really tiny change, that really small h. And so how do we do this? We go, well, the slope at some point x, m is slope, is delta y over delta x, right? And then what we're going to use is we're going to use this idea that we've pushed this really, really close, and we're doing this slope formula. So we're finding the slope of the tangent line of the parabola at y equals x squared. So just to be clear, we're not really finding the slope of the line, we're finding the slope of the tangent to the line there. Right, so we're going to find the slope of this line right here that comes and hits it and is tangent, only touches it in one point. And then we're going to go delta y over delta x, and from our previous looks right here, that's this right here, okay? And so we come back, and it's f of x plus h minus f of x all over h. That's our average slope. And so then when we plug this in, this becomes f of x plus h is x plus h squared plus x squared over h. And then that will equal, we square that whole thing out, that's going to be x squared plus 2xh plus h squared minus x squared over h. So we have x squared and a minus x squared, so that's going to cancel, okay? And then everything has an h in it, so we can actually cancel out an h from everything, and that'll just give us 2x plus h. And so that would be, essentially, that's our result for any q that we might pick. So our q might be way up here, and that would be the slope of that line right there. But what we want to look at is as h goes to 0, then this will become m of x, our slope at x, is going to become 2x. Because h is going to get so close it basically becomes 0. And so then our slope at x equals 2, right, because we want the point 2, 4, is going to be m of 2, which is just 2 times 2, which is just 4. So the slope of our line tangent at that point is 4. And then they ask us to write an equation for it. Well, to do that, what we need to do is basically just say, hey, y minus y1 equals m times x minus x1, just like that. And so this would be, we know it goes to the point 2, 4. So this would be x1, this would be y1. So this would be y minus 4 equals, our slope there is 4, so we'll put a 4, 4, and then this would be x minus 2. And if we start rearranging this a little bit, we'll get y equals 4x minus 8. That's multiplying the 4 through. And then add the 4 to both sides, plus 4. We get y equals 4x minus 4. And that should fit us right there. Should fit us right on this. And if I had drawn this really nicely, you would have seen that, you know, we would have had this nice curve like this. And then this would have come through and hit at -4. That's our y-intercept. There's our y-intercept. And at a slope of 4, and would have come through and done just like that. And hit right there. So if you have a graphing calculator, try plugging both those in. Try plugging in, you know, put in your graphing calculator y equals x squared, and put in 4x minus 4, and you'll see that it will hit it right at the point 2, 4, and it will go up and hit it in just that one spot and be tangent to it. So give it a try if you want, or just graph it out really, really nicely, and you'll find it. All right, and then the slope of this line right here, delta y over its delta x, would just be, you know, that 2 that we came up with. Oh no, we came up with 4, sorry. With the 4 we came up with right there. Okay? So try graphing that on a graphing calculator and you'll see. Next page, this is just about the same thing, and it's about finding the slope of the parabola there at 2, 4. And you can see they went through and did it as well. And, you know, you end up getting this 2 plus h squared. And anyway, they work it out there for you, and you can see it tangent to the slope equals 4, which is what we came up with, and everything. Okay, and then on the next page, instantaneous rates of change. Here we got figure 2.5. Now this one's totally worked out for us. We've got the answer right there. So basically what they're doing is figure 2.5 shows how the population P of fruit flies grew in a 50-day experiment. The number of flies was counted at regular intervals. The counted values plotted with respect to time t and the points joined by a smooth curve find the average growth rate from day 23 to day 25. So they start at day 23, that's this point right there, and then they end at day 25, that's this point up here, and they just simply draw a secant line between the two of them, this secant line right here, and they find the slope of it, because the rate of growth, the average rate, anytime you see that, like when they talk about the rate of something, they almost always mean divide by time. So if you see rate of change up or the rate of this, a lot of times it's divide by time. So we're basically going to divide the vertical axis by the horizontal axis. That's simply slope. So delta P over delta T would just be the 8.6. Would be this 8.6 flies per day. That was the average over that time period. But what if instead they had asked how fast was the population growing on day 23? Well, you could have started with day 23 and day 45, just like in the previous example, and you would have gotten the slope of this line right there, and that would have told you what the average was over that time. But then you could pick a day that was closer, and you could have gotten the average slope right there, which would be right here. That's that one. I guess I should have colored it in. Here's that yellow average line. Or you could have gone to the next one, which is that one right there. Okay, that's this one. Or ultimately, I won't even try to color that one in, I don't think, because it's getting kind of mush. You could have gone over to, let's go with this light green. We could have gone over to this point right there and gotten this one. Okay, and that's getting closer and closer and closer. And if we were to just keep pushing it back closer and closer and closer, we'd get more and more accurate representation of what the actual slope is. So if you look, essentially what you're seeing is, here's the curve, right? That's our fruit fly curve. At day 23, this is the slope of the line tangent to that point. Okay? And what you see is you start over here, and you get that slope, and then you get that slope, and then you get this slope. And then when you take this last slope, you notice it's getting closer and closer to the actual slope at that point. And so as we keep pushing the points closer and closer here, we get closer and closer to the slope of the tangent line at that point. Okay? So last thing, let's take a look at a summary of what we've done so far here in our concepts of calculus. So concepts of calculus help us in studying change of objects. This was the big thing with calculus, is we got to look at things that weren't just staying constant all the time, but were changing. Specifically, calculus helps us understand how a change in one quantity is related to a change in another. So it's a lot about changing things, right? Again, it's not that old static algebra where it was always staying the same and stuff like that. We're going to look at, we can dive into how things change more adequately. For example, how does the speed of a falling object change as a function of time? That's one of the things we were just doing. So we're going to use limits. That's where we were taking and saying, now let h go to 0, and we're going to use these limits to describe the way a function varies. Some functions vary continuously. Meaning small changes in x produce only small changes in f of x. So we do a tiny little nudge in x, and we get a tiny little nudge in the output, tiny nudge in the input, tiny nudge in the output. Other functions have values that are discontinuous. Continuous, yeah, something like that. Or jump, or tend to increase or decrease without bound. Okay? Average rates of change are calculated by finding the slope of a secant line. Right? That was, here's our curve. There's our secant line. That was how we got average, was the slope of a secant line. And then instantaneous rates of change are calculated by finding the slope of a tangent line. And so again, try to draw like same curve, and this time we want the slope of a line tangent to it, like that. Okay? Of a tangent line of a point on the curve. Okay? That's pretty much it for 2.1. Thanks a lot.